I'll try to give some perspective on this question. So let me say from the start that this idea is certainly not one that comes from me. It has a rich, at least 40-year history, and many people have been involved in thinking about this. So today I won't be able to give a comprehensive history of this suggestion, but what I hope I'll do is kind of remind us of the frame that we're working in here, the current nonproliferation regime and its challenges. I'll say a little in general about how neutrinos might enter that picture, what they could offer. And then I want to focus on a select set of hypothetical, let's say, use cases for neutrinos within the nonproliferation regime. Some ideas for monitoring nuclear explosions, weapons tests, for looking at nuclear reactors where fissile materials would be produced, and then maybe looking at irradiated fuel, which could be a stage between the reactor and a nuclear weapon. And then I'll try to pull out from that a few observations I think might set the direction for how we continue to think about this question. So let me start with the problem, as a good physicist would do. Certainly among the panelists here, I'm not an expert on the nonproliferation regime. So I think what I want to say in summary here is that this isn't really a conventional physics problem. So of course, a really political framework that we're trying to make a contribution to, a network of agreements, international laws, organizations, which I think we can maybe best say is supported by physical measurements. It doesn't consist identically of physical measurement systems. And as we've heard somewhat already, the primary organization for verification of the nonproliferation regime now is the IAEA and its safeguard system. For the Comprehensive Test Ban Treaty, which separately seeks to prevent more nuclear explosive testing, there's a technical verification system of its own, and then nations obviously have their own individual technical means, satellites, et cetera, for gathering data about one another's nuclear activities. So I just want to kind of address a question that was just asked about, well, what exactly is the IAEA looking at how stringent are its requirements right now, so we can get some frame of where neutrinos might come in. And there are way too many numbers here for you to digest quickly, which is sort of the point. But let me just bring out a few numbers. So the IAEA right now is looking at well over 1,000 nuclear facilities, including several hundred nuclear reactors worldwide. And it's checking on the agreed operation of those facilities using many different types of techniques, using seals on critical materials, using in-person sampling, non-destructive assays of fuel and other materials at reactor sites, surveillance cameras, satellite imagery, a whole network of observations. You can see extremely large in number. And all of this is being done for less than $200 million US annually. An IAEA affiliate, I think, put it really memorably that the annual budget of this whole verification system is less than the budget of the Boston Police Department. So it's an extraordinary amount of technical verification going on for quite a limited budget, which is, I think, something we neutrino physicists really need to keep in mind from the very beginning. To give a little flavor of the nuclear test ban, well, okay, so this treaty isn't enforced, but there's already a verification system if it were to take force, and it's already doing a monitoring task. This system, consisting of seismic, hydroacoustic, infrasound sensors, covers the world, hundreds of sensors, can monitor the world for explosions down to a kiloton of yield, so a very low yield. This whole system was built for about $1 billion and has an annual operating budget not too different from the IAEA's. So if we think about ways this regime could be strengthened, in a way, verification is actually a relatively strong piece of the framework. I think, as we heard from Zia really eloquently, the challenges to the nuclear nonproliferation framework worldwide maybe involve verification in part, but are much bigger than that. I won't read these again. I want to echo a lot of the points that Zia made about where we really need to be focusing future energies. In any case, some of these do have a verification technology component, and that would seem to be what neutrino detectors could try to strengthen. So what I'm showing here is potential places in cycle of nuclear activities leading to weapons where neutrino detectors could play a role. So these are places where there's fission or fission products, namely explosive tests of weapons, nuclear reactors producing plutonium for weapons, or fuel taken out of those reactors on its way towards potentially becoming a weapon. So in all of these cases, there either is fission happening or there was fission happening, and this is why there are neutrinos. So the neutrinos, as you know, don't come from the fission process itself. They come from the beta decay of fission products. And there's typically about 6 beta decays following one fission. So each fission leads to about 6 neutrinos, technically antineutrinos in the electron flavor. The Q values of these beta decays are up to a few MeV, so the neutrinos are ranging up to a few MeV. And all these fission sources are isotropic sources of neutrinos. So that means there's an inverse square law here when we think about the neutrino flux, which, as you'll see, can become very painful if you try to detect the neutrinos from far away. So you've started to get a sense here of what neutrinos can tell us about a fission source. So depending on which kind of nucleus, which isotope is fissioning, there's a different distribution of fission fragments. I show here on the left the difference between the atomic mass number of fragments coming from uranium-235 in blue versus plutonium-239 in orange. So you can see that the distribution of fragments is different. In the case of plutonium, it's a little closer to stability. And what this means in terms of the beta decays is that there are fewer beta decays occurring for plutonium-239, and they're occurring with a somewhat different aggregate energy spectrum. So on the right, I show the detectable neutrino spectra from uranium and plutonium sources per fission. So you can see there's a difference in rate depending on the isotope, and there's a difference in shape. So looking at the neutrinos emitted by a fission source, we get some sense of the intensity of the source, its strength, and how far away it is, and the fissile composition of the source. And of course, the important thing about neutrinos is that they pass through matter. So we can detect this signal in principle remotely and in quasi-real time. And in some cases, we can maybe get some information about the location of the source. But I want to note that the directionality available in a neutrino signal usually depends on having a very large ensemble of events. So you'll see in small signal cases here, that will be difficult to achieve. We've actually been detecting neutrinos from fission sources for quite a long time. The original detection of the neutrino was at a plutonium production reactor back in the 50s, and it used this process, inverse beta decay, which is kind of now the workhorse of basic neutrino physics with fission sources. So the neutrino interacts with a proton producing a positron and a neutron, and both of these signals can often be detected. So this is a pretty specific low background process. Of course, it's low cross section. So detectors for neutrinos from fission tend to be large. I show some examples here that we're looking at neutrinos from reactors for basic science. CAMLAND is a detector in Japan that's a kiloton of liquid scintillator. The liquid scintillator is useful because of the large number of free protons and because both the positron and neutron signals can be visible in photomultiplier tubes. Detector like CAMLAND was very important in the early study of neutrino oscillations. Those studies were continued by somewhat more medium-sized detectors, such as Double Show and others. Right now, there's an amazing detector under construction in China that'll continue the oscillation physics program with a 20 kiloton scale liquid scintillator detector that's looking at neutrinos from reactors some distance. One thing to note about these detectors is that they're all, with one exception, very far underground, and that's to limit the backgrounds coming from cosmic rays, production of neutrino mimicking events from cosmic ray muons. The one exception to that, and there may be some more exceptions coming online, is the detector at the bottom called Prospect, which is both smaller in size and segmented, and the segmentation allows this detector to operate on the Earth's surface with relatively little contamination from cosmic ray backgrounds. So in detectors like these, we've now had great progress in basic physics. Over 5 million reactor neutrinos have been detected since that first detection back in the 50s. But if we want to go to extremely large scales with neutrino detectors, liquid scintillators are probably not the best option, both in terms of cost and environmental compatibility. So people have started to think about using some of the very largest detectors that neutrino physicists have now and making them a little more suitable to fission neutrino detection. So you've perhaps seen pictures of Super Kamiokande, which is a truly enormous, impressive neutrino detector in Japan. It's been operating since 1996. This is a 25 kiloton water Cherenkov detector. That's a small boat going around to clean the photomultiplier tubes. It too is underground, about 1 kilometer underground, and cost in the 90s about $100 million to build. If you think back to the budgets associated with nonproliferation organizations, I think that already starts to put things in perspective. There is a much larger version of a water Cherenkov detector planned in Japan. This is Hyper Kamiokande, which would be about 10 times the size of Super K, sort of on the scale of the Capitol in height. That project is about a $2 billion project. So I think it's interesting in a sense to compare the scales of verification for the nonproliferation purpose and cost with basic science budgets, and I'll come back to that a little bit later. So recently, there's been increasing interest in maybe smaller detectors for neutrino physics, including coherent scattering detectors. So coherent scattering is a process where a neutrino interacts with a whole nucleus, scatters off the nucleus as a whole. This has been compared to scattering a ping pong ball off of a bowling ball. So it's an extremely low energy signature. For fission energy neutrinos, tens of electron volts. The observation that was made a couple years ago was at a higher energy than what fission neutrinos provide, so a somewhat easier to access signature. The advantage of trying to use this signature to look for neutrinos from fission is that the cross-section is, as you can see indicated on the right here, maybe 2 to 3 orders of magnitude higher than inverse beta decay, depending on the target material. There's also no kinematic threshold to the process, so in principle, one can access signals below the inverse beta decay threshold, which would allow looking for neutrinos coming from plutonium breeding in uranium fuel. The signal here is obviously much more challenging to get at than the inverse beta decay signal. In fact, hasn't been detected for fission energy neutrinos yet. So I won't say too much more about coherent scattering, except just to give one size scale. So let me talk now about the 3 places that neutrino detectors could in principle offer a new verification tool. And I'll start with the idea of looking for nuclear explosions. So one question here is, how well can neutrino detectors find evidence of nuclear weapons tests that would be missed otherwise by the CTBT network? So we can start thinking about the neutrino signal from a fission explosion, which is large. This was recognized in the early days of neutrino physics. Indeed, the first idea for detecting neutrinos at all was to use a nuclear weapon test in this early days of Los Alamos. that was not actually done. In fact, no neutrinos from fission weapon tests have been detected to date. After the conclusion of the CTBT in the late 90s, people started looking again at whether neutrinos might provide something of use here. The idea is that most of the neutrinos are released within about 10 seconds after the fission burst, so we'd be looking for a burst of neutrino events in probably a very large detector. Now let me give you a sense of how large a detector would be needed. I mentioned that the CTBT network currently has a threshold of about 1 kiloton of explosive yield, so it can see explosions down to about 1 kiloton. I'll give an example here of a much larger yield to give a sense of how difficult it is to get to get any neutrino signal. So here, if we look at the most recent, largest North Korean nuclear test, this could be estimated at about 250 kilotons. We'll just say that's all fission yield or close to. If we look at how difficult it is to detect neutrinos from that test in that largest water detector that I showed, Super Kamiokande in Japan, the distance the neutrinos travel is a little less than 1,000 kilometers. And it turns out that there's less than a 5% chance of seeing a neutrino from that even 250 kiloton explosion in this extremely large water detector. Now, to go back to the coherent scattering case, if you're thinking that maybe this new channel gives us a much better handle on these neutrinos, even with a 3 orders of magnitude cross-section enhancement, we'd still need over 10 tons of an ideal coherent scatter detector that's sensitive down to electron volt energy. So this is sort of cryogenic semiconductors, not quite conceivable on the 10-ton scale. So I think the idea of detecting nuclear explosions from a long range that are below the current CTBT threshold is extremely difficult. But one thing we've looked at is the possibility of not detecting otherwise undetected explosions, but trying to provide some confirmation of the fission nature of a potential explosion signal. So the idea is the seismic network detects something which seems to be a nuclear explosion. We want to increase the confidence that it really was a nuclear event, not, say, an earthquake or a chemical explosion. So the idea here is to take a putative signal from a seismic network and use that to cue a large neutrino detector. Look for, in this case, even a few neutrino events in that 10-second window, and use that as confidence that the observed explosion was a fission event. So even in this case, which is a little bit lower requirement than detecting an undetected event, we find that the size of detectors that would be needed is as large as that US capital size detector or larger, depending on the standoff distance. So what I'm showing here is how large a detector would need to be in order to detect or confirm the nuclear nature of explosions of different yields as a function of distance. Hyper K being that very large detector, sensitive to the fission nature of an explosion only for very large tests and to well under 1,000 kilometers. So clearly looking for nuclear explosions with neutrinos is extremely difficult, and I think looking at the size of detectors needed, clearly billion-dollar scale, much larger than the cost of the entire observation network already. So what about reactors? So one question is, can we look for reactors from a long distance? And one way to transition from thinking about explosions to reactors is just to think in energy units. So 1 kiloton of explosive yield is roughly equal to a gigawatt hour in energy units. So observing a gigawatt nuclear reactor for an hour, or you can think observing a smaller reactor, maybe more suitable for a small plutonium production program, observing that 50 megawatt reactor for 1 day. So the signal from a reactor is not vastly larger than the signal from an explosion, but the idea that you could monitor it for a longer time maybe leads this to being a little bit more feasible to think about. However, what's special about explosive signals is that all the neutrinos occur within a relatively small amount of time. So looking at a reactor where there's a quasi-steady state emission is a much more background challenged situation. So backgrounds here, I mentioned there are cosmic ray-induced backgrounds, but neutrino backgrounds are also a challenge. The beautiful map here is showing the expected neutrino emission from radioactive decay in the Earth mantle and crust, as well as the neutrino emission from known declared reactors worldwide. So in some sense, all of this is a background to looking for new undeclared reactors with neutrinos. And that really makes the reactor case, in my opinion, basically as challenging as the explosion detection case from long distances. So here's an example that was worked out of trying to say, accept this large background and accept the very large size of detectors that are needed, and just say what would be needed in terms of a neutrino detector in order to detect a relatively small plutonium production facility, for example, undeclared in North Korea. So the example here is looking from just over the Chinese border, putting aside the political feasibility of this, at a new reactor at the Yongbyon site in North Korea. For a 10 megawatt reactor viewed from this distance of only 130 kilometers, this requires a 10 megaton water Cherenkov neutrino detector that's buried about 1 kilometer underground to reduce backgrounds, that sits for 1 year. This would allow the measurement to be made. So this is extremely difficult, I think, really on the scale of the explosion detection. There is nonetheless a program underway to try to look at this challenge. This is a more modest example, looking for a larger reactor, so a commercial power reactor that's 1,600 megawatts from a distance of just 25 kilometers. In this case, this project called Watchman in the UK is only a kiloton detector. It's 1 kilometer underground. There's an existing mine here. And it's able to say within about 2 years that there is a second reactor turned on this site. There are 2 reactors here. So that's about how long it takes to find, in this sense, a sort of undeclared reactor on a known reactor site. Again, quite challenging. But I think there's another way to look at this scenario. What this is demonstrating is that it's possible to get some information about a reactor site at distances of up to tens of kilometers with detectors that can actually be built for on the order of tens of millions of dollars for a large detector like this. Now, I think naturally where this is going is saying, why do you want to be 20 kilometers away from a known reactor? If you can get closer, you can certainly get by with a smaller detector. So there was interesting work done around the time of the JCPOA looking at what could be done for the heavy water reactor at Iraq if a neutrino detector could be placed just right outside the reactor building. So in this case, a detector that's only modestly better than current capabilities in terms of background rejection at the 10 to 20 ton scale could do an interesting task, differentiating between a normal operation of that reactor and a case where there's been a clandestine refueling, so a removal of fuel in order to remove plutonium and a new core being inserted. So what you see in the simulation here is the difference between the neutrino spectrum observed in the case of normal operations allowed by the agreement in blue versus a case in which there is removal of plutonium that would not otherwise be discovered, say there's an outage in other monitoring capabilities, that's black, and there's a difference observable in the spectrum shape, even without rate information when it comes to neutrinos. So this is an interesting capability at sort of a smaller scale using detectors that are just a little bit beyond where we are now. But a bunch of us in neutrino physics thought that it would be interesting to say, let's look at the detectors we actually have now coming from particle physics and say what those really existing detectors could do in the case of North Korea as a verification measure. So a group of us, including neutrino physicists from South Korea, China, Russia, Japan, and Europe, got together and just stuck with current capabilities of, this is in fact that small detector, the 4-ton scale surface operating detector. And we looked at what this could do as a verification tool at the Yongbyon site in North Korea. What I show here in the inset is a concept of how this detector could look. This is about the size of a real detector if it were placed in shipping containers, could be brought to the site on a truck. And using the demonstrated performance of this real segmented scintillator detector, we show that there's actually a really interesting amount of verification work that could be done at Yongbyon. So for example, with a detector that's right outside the main plutonium production reactor that's operated there for a few decades, we could, in less than 2 weeks, detect an unauthorized startup of that reactor if there's an agreement for the reactor to remain shut down. There's an experimental light water reactor on that Yongbyon site that has not started operation yet. It too could be monitored with a similar size system to what I've shown you. In that case, if there's an agreement not to operate the reactor, an unauthorized startup could be detected with neutrinos in less than a day. If there's an agreement to allow that reactor to operate, the operation could be monitored similar to that Iran case, and a neutrino detector outside the reactor could indicate diversion of plutonium from the core in a relevant amount of time. It's also possible to try to move the detector a little bit further from the reactors to be even more, even less intrusive from a North Korean perspective. This also can be done with existing technology for orders $5 to $10 million. So still quite expensive, but not getting to the billion-dollar scale of the previous cases. So I think it's still important to put this reactor monitoring capability in the context of existing capabilities. So we know that if a few percent of the energy of reactor escapes in the form of neutrinos, it's really over 75% of the energy that escapes in the form of heat. And this is certainly visible in many satellite images, just an example of Yongbyon. But as has been pointed out, this isn't a totally precise indicator of the reactor state. It certainly doesn't give any information about the fissile content. So neutrino detectors may still have something to add in terms of precision and persistence. Also, neutrino detectors, compared to full IAEA monitoring, which is certainly an option and has been used in the past at Yongbyon, meet in a much better way this desire for less intrusive monitoring. They can be outside of the reactors, requiring no people on site once they're installed. So I'll come back in a moment to an additional benefit, possibly, of using neutrino detectors at a site like Yongbyon. But let me just say about the case of monitoring spent fuel. That possibility has also been looked at with neutrino detectors. Spent fuel, given its slight radioactivity due to long-lived fission products, is a much lower producer of neutrinos than an operating reactor. But it's still possible with a sort of 10-ton scale detector and a year observation time to detect some large level of diversion of fuel from a spent fuel, so say dry cask storage facility. In any case, you can see that trying to talk quite honestly about the capabilities of neutrino detectors in this context, it's really difficult. And actually, I think maybe the thing that's most promising, most interesting to talk about is the reason that neutrinos would usually come up at an APS meeting, which is just that they're very interesting for physics. In fact, the word neutrino did appear in the Iran deal. It was in a segment on possible areas of civil cooperation between Iran and the other parties in the agreement, including neutrino astronomy. And the idea that science could be done with these verification detectors is certainly a part of the Watchman program, which has possibilities for looking at new neutrino physics, for doing neutrino astronomy, looking at neutrinos from supernova. And I would say, in a way, what's probably the most unique and special element of the idea of putting neutrino detectors at Yongbyon is that they could be an early step in re-engaging North Korea in the rest of the world, particularly in the scientific community. We think that building a neutrino detector, like what I've shown here on the site, can be done with North Korean participation. This doesn't require any classified information or entrance into the reactors themselves. So this might be a place to start to get teams to work together. We can imagine even expanding a program like this to have similar verification tools in South Korea, power reactors there, having a program of neutrino physics starting to involve both North and South Koreans. Indeed, in this project, the involvement of South Koreans and Chinese scientists has been a really strong piece, and we think that the possibility of connecting, in this example, North Korean physicists with the broader physics community is something that really might make this actually make sense. So to this difficult question of whether neutrinos can strengthen the nonproliferation regime, I mean, I think it's clear from what we've heard that what neutrino detectors offer, and particularly at the cost that they come, is unlikely to be really transformative for nuclear verification. Nonetheless, there may be some niches that are worth exploring. I think looking at explosions versus reactors versus spent fuel, it's clear that reactors are the most promising target. You can get sort of close to them, and they have a reasonable neutrino emission. Clearly, being closer to reactors gives more ability to look at the fissile material content, and to not have such a large detector. And I really think that this idea of non-intrusive verification combined with scientific engagement is maybe the thing that neutrino detectors can offer in this space. So I'd say, neutrinos have surprised us many times, and I hope we can be open to some of these possible niches, and let's see. Thank you.
Questions or comments for Rachel?
Hi, thank you. Very interesting talk. I'm not in the field of neutrino detection, but I wonder if you can give sort of a sense as to how quickly are our abilities to detect neutrinos moving forward. Is it kind of a very slow pace, or is it moving quite rapidly? And then how would that affect maybe some of these detection times that you cite?
Yeah, it's a good question. The real limitation here is the physics of neutrinos, that the cross-section is just low. That said, there has been recently a lot of progress in these surface deployable detectors motivated by interesting basic physics, and so that leads to some more deployable near-to-reactor options.
Yep, thank you.
That's really reducing the backgrounds.
Okay. I used to work on neutrinos and have a lot of colleagues building neutrino detectors near reactors. And what I learned is that you need permission to even build a detector that's outside of the reactor camp. Okay, and I can imagine in North Korea political system, it's a totally top-down, so it's not like the physicists themselves can propose, okay, I want to build it. It's like the very top needs to agree with it. So how do you think this can really happen? Because I do think this is a good idea.
I completely agree. Yeah, the idea is that this would be agreed to, as an early step in the top level or higher level political negotiations, for sure. I mean, it's not possible to have contact with North Korean physicists without that.
I hope this isn't a silly question, but on slide number 19, I think it was. Yes, could you explain why the ocean is so dark? Because I can imagine there might be some hot spots that you would see there.
Yeah, I mean, it has to do with the crust thickness, that it's thinner in the non-continental areas. So this is there is some emission of neutrinos from radioactive elements in the Earth. There's less in the oceans because there's less crust material. This is what would be visible on the surface.
But what I'm referring to, there are some machines that, do they move too quickly for you to see them? Or, like, for example, a submarine with a nuclear reactor in it. That's what I was curious about. Would that show up?
Yeah, I mean, I think if you're interested in submarines, the cases like this, really. I mean, there may be, say, 100 megawatts instead of 10, but enormous detector for even 100-kilometer standoff. So I think monitoring the open oceans is extremely difficult.
So if there aren't any further questions, let's thank Rachel again. A fascinating talk.